Okay, welcome back, everyone. So before we go into, before we start our class, I want to briefly mention. Final exam that I think you guys all received the. I guess you guys all received the email yesterday that the exam will be posted, before Thanksgiving, and then you will be given roughly a little bit more than 10 days to finish it. And then from the feedback I saw from previous 2 years, students tend to think the final exam is slightly easier than the midterm. And then, but then this year might change a little bit because last year I have more than half of the class score more than 90, and then it gave me a horrible time to assign a letter grade. So that I will add one more problem this year, that hopefully we can kill most of the 90 points. Okay, and then and the second thing is about the homework solution. So right now, I observe a tendency that some of you did not turn in your homework, which is actually fine. There's a story that I normally don't tell people because it sounds like show off, but in my high school and middle school, I rarely do homework. The reason is because sometimes I think homework is useless. And then, I usually just look at the answers before the final exam and I went ahead with the homework. So that's fine. But then, of course, as a class, we want to reward students who did homework, right? So right now, if you guys notice, I haven't posted any homework on a homework solution on our Collab site. And then, some of you who finish your homework receive the homework solution in your folder. So this is the way we're going to do it, right? If you do the homework, you will receive the homework solution earlier, and then you'll be able to study the solution, okay, and then find out, if there's anything wrong, and then also find out, also if you don't understand something, you can have the chance to ask questions in office hour. So for those of you who prefer not to turn in the homework, you will still receive the homework solution, okay, together with the final exam. But then you won't have any chance to ask questions because the exam is posted, then I can't answer anything because then it will be unfair to other students. Okay, and then finally, it's about the course evaluation. This is the part that I hate UVA. Okay, is that 3 years ago I was a student, right? So I'm not that far away from being a student. And then I remember I never did any course evaluation. Is because the reason is very simple, right? Unless the instructor is terrible or terrific, there's really no reason to comment on the instructor. And but then UVA has this strange policy that if there's not enough students participate in the course evaluation, they will simply think that the faculty did a poor job of engaging students in this class. Okay, and I do want to say one thing is that if you do want to pass this class, you have to turn in your final exam. I know that some students, try to test my limit, try to test my boundary, especially some student in 4th year. Okay, I've seen this before. Now let's come back to the class. Okay, last time we briefly explained, what is entanglement. And then entanglement, we briefly say that, if a state, you can write down a state as direct product of individual particles, then it's an entanglement state. And we give a very simple and popular example is that, is this state a superposition of 2-qubit state. So this one, if you measure, you measure particle 1, if particle 1 happen to be in ground state, then the second particle will also be in ground state. And then if the particle 1 is in excited state, then the particle 2 is also in excited state. So this is quantum correlation, built-in quantum correlation. And then I want to make it very clear, the quantum correlation is different from classical correlation. because the difference here is actually lies in the superposition, right? For example, you can say that there is certain correlation. If, for example, if I throw this and it hits something and then the other thing will fall. Okay, this is classical correlation. But then classical correlation is similar. Well, the way I would put it is that the similarity is similar to flipping a coin and then the Schrodinger's cat, right? The difference is like when you flip a coin and then the coin stops, and you can take your time to decide when you want to look at the result. But then when you look at the result, actually doesn't change the result itself, right? After the coin stop, if it's head, it's head. If it's tail, it's tail, okay? But in Schrodinger's cat, the cat state is not determined until you look into it, until you do the observation, right? And then you collapse into one of the eigenstates. So here is the same. Okay, here is the same. That before you do any observation, particle 1 and particle 2, they are in this superposition state. So they're 50% 0, 50% 1. Okay, and then until you do this measurement, then you start to see. Okay, then you start to see. Okay, if the first particle is 0, second will be 0. First particle 1, second particle also be 1. Okay, so this is the difference between quantum correlation and classical correlation. Now I want to introduce something that people use a lot in talking about entanglement, and also this is a tool for you to play the devil's game. Okay, the devil's game. If you guys remember, there are 3 of you, okay, who are really unlucky, have to play, so that naturally you need 3 particle states if you ever want to participate in that game to win that game. And then the physics, well, the quantum thing that you will use to win that, well, to help you win the devil's game is the electron spin. Okay, some of you might have heard of it, some of you might not know what it is, but then that's all fine because you actually have used it in your homework. Okay, I don't know if you guys remember this, the Pauli matrix in, I think it's in homework 6, right? You guys have all calculated a little bit of Pauli matrix. Okay, and then I think in the homework you are asked to verify the Pauli matrix. They are Hermitian, and then I think you are also asked to verify that the square of this Pauli matrix are actually identity matrix. Okay. When we write down something in a matrix, it's fine if you drop the little hat here because it's implied that it's actually the fact that it's a matrix implies that it's an operator. And you were also asked, I think, in the homework to show that, okay, if you multiply two of the Pauli matrix together, these are not Hermitian anymore, right? These are non-Hermitian. So this is what you guys learned in the homework. Okay, something that I didn't ask you guys to calculate, but then it's extremely useful, is that it's a very cool commutation relationship between this Pauli matrix. And the commulation relationship between x and y, okay, matrix x times y minus y times x. This one you can refer to note page 11. Okay, give you 2 times I and then Pauli matrix Z. Okay, you can easily verify this because this is simply a 2 by 2 matrix. And then you can also see that Y commute with Z give you 2I x, and then Z with x will give you 2I y. Okay, so this is actually a very, very interesting commutation relationship with a little bit of kind of symmetry here, right? The two commutation will give you the third one. Okay, and then for those of you who have done the bonus question in homework 6, this might actually look familiar to you, right? Because in the homework bonus question, you are asked to calculate the commutation relationship in the angular momentum, right? Angular momentum is the position cross product with the momentum. Okay, anything that rotates actually has, well, depending on the frame. Okay, but in general, when something is rotating, and then we will consider angular momentum. But anything can have angular momentum, and there you actually verify that for angular momentum because it has three directions, right? X and Y and Z, and then you can actually show that I H bar L Z X okay, so see that the commutation relationship for angular momentum, and by the way, if you want to know how you can derive this, you can look at the textbook. Okay, I think there's a chapter called angular momentum, and I actually show you this. And for the angular momentum, okay, you actually have a very similar commutation relationship. When you commute two of them, okay, it gives you the third, and then there's an I there. Okay, and of course there's a constant, but then you can always normalize a constant. It's something very easy to get rid of. So from here, what you can tell is that it looks like, the Pauli matrix. Okay, the Pauli matrix. It looks like they're describing something that's related to angular momentum, right? Because they satisfy the same math. Okay, and now the only difference here you can see is that, okay, there's a H here, and there's a 2 here, right? And then you can actually get rid of this by going with this definition. Sx to h bar divided by 2, 6x sy to and sz. Okay, and if you go with this definition, then you can easily see that xx, sy, sz satisfy the commutation relationship of an angular momentum. So from a mathematical point of view, it's impossible to tell the difference whether you have to say, okay, this is something related to angular momentum because the math is the same, right? It's the same way as we say that when we do the quantization of photon, and then you get a Hamiltonian that looks like harmonic oscillator. You have to say that these two are the same from the fundamental level because, when you solve the equation, they give you the same answer. Okay, so from here we can see that this Pauli matrix actually represents something related to angular momentum. Okay, now let's take a look at what they are, right? And then the simplest thing you can do if you look at it, right? This is a 2 by 2 matrix. You can do whatever you want. For example, very simple, you can just do a quick calculation and then get the eigenstate and eigenvalue, right? They kind of tell you, okay, what it is. So that what you can do is that you can the way to solve this is lambda x The way to solve this, it's in the node, but then it's fairly trivial, right? 2 by 2 matrix, you multiply them, and then left-hand side equal to right-hand side. You assume psi x is alpha and beta, and then you can solve this. And then the solution here you get is that lambda x is plus minus h bar divided by 2. Okay, this makes sense. It's because if you look at sigma x squared is the identity matrix, which means if you try to get the if you want to get the eigenvalue of sigma x squared, you will get 1, right? You will get 1 because it's identity matrix. So now sigma x squared's eigenvalue is 1. It means sigma x eigenvalue can be 1 or minus 1, right? Because both of them, when you square it, give you 1. Okay, so it's not surprising that here you get plus minus 1 times h bar divided by 2. Okay, and then the corresponding, where's my note? Okay, and then the corresponding eigenstate, we call it, for example, we can call this x plus. It means we're solving the eigenstate corresponding to a sigma x or sx, and then plus means that we're taking the plus, the positive eigenvalue. Okay, so the eigenstate corresponding to the positive eigenvalue, I think it's 1, 1, yes, 1, 1, and then x minus is 1 minus 1. Okay, and then you can do the same for y and z, and then you will see that all the lambda, all their eigenvalue are all plus minus h bar divided by 2. Okay, which is not surprising because if you look at them, they're all 1 or minus 1, and then maybe I is just 90 degrees off of 1, and they're just at different position. So then when you do the eigenvalue, okay, it's not surprising that their result is the same. And then I can probably write it down here is psi y plus equal to (1 minus 1). Okay, and all these are all just math. Okay, it doesn't, at this point, it doesn't have any physical meaning. Okay. Okay. Let's see. Let's erase this part. Now, let's see what would happen. Okay, well, let's see if we treat this S operator as something that's measurable, right? Because it's Hermitian operator, it corresponds to something that's measurable. Then we can kind of see, okay, what would be the measurement result, right? If you measure it on x direction, okay, we call x direction is corresponding to this sigma s, x is the x direction. Then what you get is that right. Then what you get is along the x direction you get h bar 2 or minus h bar 2. Right. There are two eigenstates, so when you measure it, you will get either one of them. Okay. And then if you measure the y direction, you also get plus and minus h bar divided by 2. And then if you measure z direction, then it's up and down. Okay. Okay. So it's an angular momentum. So what it is that from the math, what you can see is that, okay, it's an angular momentum. And then when you measure it, the magnitude is always the same. No matter which direction you choose to measure it, the magnitude is always h bar divided by 2. And then the quantization is binary. Okay, it's either pointing up or pointing down. okay, pointing up or pointing down. And, and in the 1920s, okay, this actually, the development, the history of this development is a little bit, well, it's not the same as what we describe here. They first think about the concept of spin and then come up with, well, let me think about it again. No, actually, Pauli actually first came up with the Pauli matrix, okay, exactly like this. And the reason he came up with this is that when they're studying the hydrogen atom emission spectrum, right? We solve it in the in earlier class, and then you can look it up in the textbook, and then you get the quantum number, okay, N, M, L, right? Because it's a three-dimensional space, you get 3 quantum number. But then in the actual experiment, people find out that there is a third quantum number. Oh, sorry, there's a fourth quantum number, S. Okay, and this quantum number is binary, either pointing up or down. Right, it's either 1 or -1. Of course, there's a unit. Later, people discover it's h bar divided by 2. Okay, and then Pauli first figured out, okay, if we use matrix representation, and then no matter which direction you measure, it's always up and down. It's always h bar divided by 2 plus or minus, right? And then the matrix that corresponding to this quantum number will be Pauli matrix. Okay, that's the discovery process. So it's actually based on experiment, and then Pauli used his intuition. Okay, he's a genius, so he used his intuition, and then guessed, okay, there must be something corresponding to Pauli matrix. And then at the time, nobody knew what really Pauli matrix corresponding to. Okay, it just agreed with the experiment perfectly. And then later, okay, this one is a funny story, is that this one is a part that later I will explain what it actually means to undergrad or to grad students. Is that later people, two graduate students, okay, came up with a paper saying that if you consider the electron itself, because where the angular momentum come from, right? Usually come from rotation, okay? And then the rotation for the electron is well described by the angular momentum itself. And then you can only have 3 quantum number because it's 3-dimensional space. So that to look for additional degree of freedom, what they think is that, okay, maybe the electron itself is spinning, right? That's a rotation, additional degree of rotation. So that's what they have in their mind, okay, if they try to draw the analogy from classical mechanics, right? So what they say is that, okay, then the electron, consider that electron is kind of a particle with certain size, and then it's doing the spinning, okay, and then with a constant speed. That's why no matter how you measure it, the magnitude of your spin is always h bar divided by 2, okay? The difference is only the direction. And so this this kind of interestingly become the name, okay, for this is electron spin, because it kind of explains to you, where the Pauli matrix come from. But then the funny thing is that this paper is actually wrong, okay, and then the reason it's wrong is that if you really use this model, you will see that the speed of the spin, okay, required to generate h bar divided by 2 angular momentum will actually require the speed at the surface of the electron to be faster than the speed of light. Okay, so you have to spin that fast. So this model is a very, very, I would say it's a good way for us to kind of, understand spin in our mind, but then it's not correct. And then the story is kind of funny, okay? The first is that I don't know which country they are in, but then but 2 grad students came up with this model. Actually, 4 grad students. They're in 2 different groups. So those 2 grad students sent out their paper, I think either to Nature or Science, without consulting their advisor. Okay, very, very brave. And then it was accepted. And then their advisor found out this paper. Okay, accepted but not published. And then the advisor immediately said, okay, but the speed of the electron exceeds the speed of light. This is wrong. And then the 2 grad students thought they made a huge mistake and are really embarrassed. And then, but then the advisor said, okay, well, it's accepted, right? So, what the hell, right? Just leave it there. And then, so that paper got published. And then later, people actually knew that there are another 2 students also, actually, I think in the United States, also got the same result at the same time, right? Because a lot of people are working on this. But they told their result to their advisor before publishing it. And then their advisor also told them, okay, the speed exceeds the speed of the light, so your result is wrong, so they didn't send out, okay? And then those 2 students, okay, who didn't tell their advisor at the first place, won the Nobel Prize later, okay, because it kind of explains what spin is, although it's wrong, okay? And then, so it's it's a type of, so this kind of is always a good story to, discuss what's the student and then their advisor's relationship should be, okay, how much control the advisor should have on their students' research. And then nowadays it's impossible to imagine, okay, students send out their paper without telling their advisor. You can literally get fired, especially in experimental group, is because your advisor has to buy all this equipment for you to do the experiment in the first place. So that's, in experimental group, it's almost impossible to do this. Theoreticians, it could be different, but usually the student would discuss with their advisor, but if they hold different views, the student can publish this paper on their own, okay, without their advisor's name on it. So, yeah, so sometimes, okay, making mistake is not that terrible, okay, as long as it's an inspiring mistake. But of course, I've seen paper that just, it's just wrong. Okay, it's not inspiring. Okay. Anyway, okay, let's come back to here. And okay, you might wonder, okay, what's the if this model is wrong, then what spin really is, right? So later in the I think it's 1928, Dirac famously figure out the equation called Dirac equation, and then in that equation, he actually the way that he want to build Dirac equation is because Schrodinger equation doesn't agree, cannot incorporate special relativity. Okay, I don't know if you guys remember this, but you guys should remember what Schrodinger equation is. Partial t. In your Schrodinger equation, right? Suppose there's no potential. Okay, let's just use this. Okay, this equation cannot agree with special relativity. The reason is you have second-order derivative on space and first-order derivative on time. And then in special relativity, it's actually a 4-dimensional space. The time and position, okay, they're actually following the same math. The only difference is that time only go one direction, okay, only forward, not backward. That's the only difference between time and position. So that people kind of think, okay, how can you resolve this? And then what they do is actually trying to make start from E equals mc squared, because that's the energy you can get for special relativity. And then from there will be 2 paths. One is you make this time derivative a second-order derivative equal to something, okay. And then this is later is become the Klein-Golden equation that describe boson. And then Dirac, okay, okay, of course the Dirac equation is not like this, but then Dirac, what he does is that he thinks, okay, you can lower this differential by 1 on space, right? Then also it will be same order for position and time, right? And this becomes the Dirac equation. And then what Dirac equation find out is that the Dirac equation, if you solve it, okay, the Dirac equation naturally will have 2 solutions. The solution will naturally be in a vector form. So one is actually spin up, one is spin down. Okay, the spin actually come up from here. Okay, so the correct way to understand spin is that spin is a special relativity effect. Okay, and then in a way you can say that okay, this picture is correct in some way, that the electron is really spinning, or you can kind of think the electron is really spinning, and then the speed of light, speed of the electron spin exceed the speed of light, which actually tells you, okay, indicate that this is actually entering the special relativity or general relativity region. Okay, so this is a relativity effect, and you will not learn this until you go to advanced quantum mechanics. Okay, so let's see. Okay, now let's answer one question. Okay, answer one question that you may or may not have now in your mind, is that then spin, right now we see that spin is three-dimensional thing, right, x, y, z, but then our matrix are only two-dimensional. Our vector are only two-dimensional, right? This is counterintuitive because two-dimensional means x and y, right? So it's only two-dimensional space. So how can you describe three-dimensional thing? Now let's take a look at this eigenstate first. Okay, the eigenstate for z, spin z, okay, z direction spin, is 1, 0, 0, 1, right? This is a very, very basic, very, very basic eigenstate we know, okay, the very basic one, so you can put it down as, okay, say this is z plus, let's say, z minus, right? You can use this to build a frame, and then it's interesting that you can use the eigenstates of z to actually express the eigenstate of x, right? You can see that these two states plus each other give you the eigenstate of x of the positive eigenvalue. These states minus each other give you a minus, right? Give you a minus. So on this chart, what will happen if they two plus each other? Then on the vector scale, this is just 45 degrees, right? So this is psi x plus, okay. And then if they minus each other, plus this one minus that one, it will give you, okay, right, 45 degrees down. So from a geometric way, you can kind of think of the spin is just similar to, well, if you only consider two-dimensional, only z and x, the spin is actually in many ways similar to the polarization of light, right? You can measure them in one, for example, in z direction, and then you get these two, and then you can rotate to x direction, and then you measure them. It looks like you're measuring the 45-degree basis, right? So in principle, you can also use spin of electrons to do the quantum key distribution, okay, assuming you can actually deliver spin over long distance. And that might be possible in the future if we really have superconducting, room temperature superconducting. Now what about y, right? Y direction. Okay, you see now this is the interesting part now. The y direction is how you build the third dimension, okay? You see that the y direction has complex number in it, right? Has complex number in it. And then the x, y, well, x and z direction are only real number, right? When you build this state, when you build this coordinate. So what it really is that z, x, z, okay. Yeah. So you can imagine that perpendicular, right, going down perpendicular to this plane, okay, you can use that axis to express a complex number, right, to express a complex number, okay. So the fact that you have complex number here give you 3 dimension. Okay, if you compare with the polarization of light. Polarization of light, you can also use 1, 0, 0, 1, and then 1, 1, 1, minus 1. But then because you don't have, because it's 2-dimensional, so you actually don't use complex number. Okay, the fact that you have complex number gives you 3-dimensional. Any questions here?
Kind of assigned a direction for the positive and negative x's and z's. Would the positive y go like into the board or out of the board?
You use the left-hand rule. So left-hand rule. So well, right-hand rule. X, y, and then this is z.
Okay.
Go from x to y, and this is
okay,
z.
So right, positive.
Yeah, yeah. So you can do the same. Okay, if you have
positive one, you go to positive z. Okay.
Yeah, yeah.
Okay.
And then yes, okay. And then now let's see one. Yes, let's see one question here. Okay, let me just write down this eigenstates. Actually, later people find out that Pauli matrix has, deeper meanings. It's actually ties with the group theory. It's when you satisfy the commutation relationship of angular momentum, and then you confine that in 2-dimensional matrix, then you will get a group, okay, and that group is described by the Pauli matrix. And then later, okay, right now there's a kind of a trend to try to re-express all the physics, at least the quantum physics and then the modern physics, with group theory. And then some people find it very beautiful, and my math is good enough to appreciate that. But I really I understand why they're trying to do this, and then hopefully that can lead us to some new physics. Okay, now let's see a question here. My question is, if I prepare the spin. If I prepare electron in spin up state, okay, spin up, z direction, positive, and now I want to measure the spin at x direction, okay, what are the possible results, right? And later you will find, okay, people do this all the time. It's not like we deliberately measure at the wrong basis, but then it's actually useful. Okay, so the way to do this is to recall our quantum mechanics postulate, right? If you want to measure a physics quantity, okay, physics attribute, then you write down its matrix. You write down its operator, and then what you do is you also write down the state. And then the state is in superposition of the eigenstate of x, right? Of the corresponding operator, right? And then this coefficient in the front amplitude square, is the probability you measure the, let's see, the eigenvalue corresponding to the nth eigenstate, right? So if we use this postulate, then it's fairly straightforward for us. And then you can see that, okay, this is the state you have. Okay, you want to express it in the eigenstate of x direction spin, right? So it's this two, right? And then it's relatively simple, right? This plus that, you cancel this, and then they two agree, right? So equal to 1 over 2, okay, psi x plus psi x minus, right? So you see that the eigenstate in z direction is actually a superposition state in x direction. Okay, so the other way you can think about it is that if you want to do hammer gate, right, you just rotate and measure, and then you get a superposition, right? And you can kind of see that if you start with psi z minus, right, the spin down state, and then what you will have is that you will have square root of 2, and then psi x plus minus psi x minus, right? So this is, it's exactly like your hammer gate, right? If you start with, for example, here, if you call this 0, right, then you get a plus superposition. If you start with 1, then you get a minus superposition. And later you will actually, people actually found it back all the way down in the I think it's 1990s, that there's a correlation between measurement and quantum gate, right? Actually, people actually have proven mathematically that entanglement plus measurement plus single qubit gate can be used to realize all quantum gate, right? So nowadays there are a branch in quantum computing is it's called measurement-based quantum computing. Okay, it's similar to this. Okay, this is a hammer gate if you think about it. Okay. Now let's make this a little bit more difficult. Right now, what you have seen is that, okay, if you have a single electron spin, right, and then you do measurement, you can convert from eigenstate to superposition. Now think about this. What if I prepare an entanglement state in spin, right? So for example, this one, I prepare it in a way that, okay, I call spin up 0 state. Okay, and then spin down is 1 state. Right, I can do that, right? I simply assign which is 0, which is 1, and then I create this entanglement state. What it means is that if I measure the spin of the first electron in z direction, okay, if our measurement result is spin up, then the second electron will also be in spin up. If the measurement result is spin down, the second electron will also be in spin down. Okay, so it's a correlation in the spin in z direction. Okay, this is what this state is. Now, let's say if I just, want to make things complicated on purpose. What if I measure the first electron in x direction? Okay, it's like I deliberately want to mess up things. I know that we prepare it in z direction, but I just want to measure in x direction. And what will happen, right? So the way to do this is very similar as what you do here. You express your state as the eigenstate of x, right? And then what you can get, okay, since we already know this here, I just plug in, and what you will get is, see, 1/2, okay, x plus x minus, and then this is z plus, okay. And here, okay, just to simplify the notation, I call z plus 0, right? Because z plus, originally we defined this as zero state, okay. And then also this one is psi x minus plus, sorry. Okay, so this is a state. And then when you want to measure the first electron, right, you see that you'd better collect the terms together, right? There's x plus here, there's x minus here, right? You'd better write them together, okay, to know what will be the result, right? So if you do that, what you will see is that you will see, okay, x plus, you have a 0 here, you have a 1 here, okay, they 0 plus 1, okay, I use 2 square root of 2 to replace 2 here, and then you can see you also have spin x minus, right, and then for x minus you have 0, you have 1, but then it's a minus sign here, okay, so okay. Now this becomes really interesting now, okay. So what it tells us is that if you want to measure the spin in x direction for the first electron, you have 50% probability of getting a positive number. You have 50% of probability of getting a negative number, right? But when you get a positive number, okay, remember this is entanglement state. When you get the positive number, then what will happen for the electron 2 is that the electron 2 will collapse into the superposition state. Okay, and then for the other 50% probability, where you measure a negative number, then electron 2 collapse into, okay, electron 2 collapse into another superposition state, which is different. Okay, so now this is interesting. Okay, it looks like, if you look at it, before the measurement, right? Before the measurement, your state is in either 0 or 1, right? Either 0 or 1, and then depending on your measurement result on z, okay, it can be either in 0 or 1. But just because you measured it in a different frame or different basis, then all of a sudden, okay, your second electron now become in a superposition state. So what this means is that what you do to the first electron can actually change the second electron. And this actually makes perfect sense because they're correlated, right? What you do on the first one will affect the second one. And does that convey information? No, no, because this is, again, the probability, right? It's 50%, 50%. You have no control of what result you can get, right? So, but this kind of tells us that choosing the measurement base actually matters in the entanglement. And second is that it's possible for me, okay, if I hold the first electron, it's possible for me to make a decision and then change the state of the second electron, okay? And you can now see where we're going for the devil's game is that we will create a 3 electron states, okay? They're in an entanglement. And then the first 2 people when they decide to do the measurement and then they get the result, will actually change the electron of the third person. And the third electron, as long as you create this entanglement state in the correct way, the third electron will collapse in the state that will lead you to win the game. Okay, so that and in this process, okay, there's no information flow. Okay, what you're simply creating is a quantum correlation that guarantee you to win the game, and that's it. Okay. Any questions here? Okay, if no, then we can let's see. We can go back to the devil's game and let me get the rule here. Okay. And I think we need, yes, we need this. And then okay, erase all this. Okay, the rule of the game is, just repeat it, is that three of you unfortunately enter the game, and then you are going into a room. Okay, each one of you going into a room. You can bring whatever you want into the room, but then the room is well isolated so that you cannot send out any information or receive any information. Okay, and then when you enter the room, you will see a card on your table, and then the card can be either X or Y, right? And then there are only 4 possibilities. Okay, this you know this before you enter the room, is that either 3 of you all receive the X card, or only 1 of you receive the X card. And then the probability of all this, happening is 25% each. Okay, and to win the game, when you receive the card, you have to shout out a number. You have to shout out either 1 or -1, right? If the number you shout out, when you multiply the number that you shout out, ABC is the number shouted out by Alice, Bob, and Chess. If it's the first situation when you receive all 3 X cards, your number, the product of the number you shout out has to be 1 to win the game. And then for all the other 3 cases, the product of the number you shout out has to be -1. Okay? And this is a very fair game, is because classically there's no winning strategy. Okay? You can't just go in there and then look at your card and shout out a number. That doesn't work. Okay? And and you're required to play this game 10 straight times, and then if you win all of them, you survive. Now, let's see how we can win this game. So the way that you can win this game is that you prepare entanglement state. You have 3 electrons, and then you have 3 electrons, and then you prepare them in this state. Okay, entanglement state. Very simple. You just add 1 more electron, and then they all like this. And then here, 0 means spin up in z direction. Okay, so it's like z plus, and then 1 means spin down. Okay, and then each one of them bring 1 electron into the room. It doesn't matter which one they bring because the initial state are symmetric along these 3 electrons. So when they go into the room, then what they do is that they look at the card. Okay, they look at the card. If the card is X, then they measure spin in X direction. Okay, let's see it as x. And then if your measurement result is positive, okay, if your measurement result is h bar divided by 2, then you shout out 1. And then if it's minus h bar divided 2, you shout out minus 1. Okay, and then the same if you receive y card, you measured it in y direction. And then, okay, if your measurement gives you a positive result, you shout out 1, negative result, you shout out minus 1. Okay, very simple. And then if you do this, okay, this will guarantee you to win the game. Okay, and then the math behind this is a little bit long, but then it's well written in the note. Okay, page 20 and 21. Let me briefly explain how this can work. Okay, so the way to think about this, for example, X game, the first situation, all three of them receive X card, right? Then what you're going to do is that now, because your state is preparing in z direction, right, eigenstate of z, but now your measurement needs to be happening on x direction. So what you do is that you express this z eigenstate, okay, with your x direction eigenstate, okay, just like what we have done before. And then once you do that, okay, you can write down your final state. You can simplify a lot of them and then write down your final state, and then your final state will look like this. Okay, if we do all measurement in x direction, here to simplify, up means 1, and then x means the direction. Okay, so the state you would eventually get is this state. Okay, simply express your state, okay, not in z direction but in x direction. Okay, and then now you can see that, okay, if the first two persons do the measurement, if the result are both 1, okay, if the result are both 1, and then you check the state, only this one are both 1, then the third one result must be 1 as well. Right, there's a correlation here. And then if the first two results are minus 1, both are minus 1, then the third one is also 1. Okay, so, and if the first two results are different from each other, okay, 1 minus 1 or minus 1, 1, the third result is always minus 1. Okay, so this way, this is a quantum correlation that guarantee you that the number you shout out is always, the product of them is always 1. Okay? And you can do the same thing for the other three situation. The other three situation is symmetric. You only need to calculate 1, okay, because it doesn't matter which one hold the X card. And suppose if the first person, Alice, hold the X card, and then the state you are going to get is okay, this is the first possible state. If you measure 1 in x and then okay, then the second one could be in 1, and the third one is minus 1. So in total, the product of this is minus 1, and then you will also see this. Okay, just flip of this 2, but then the product is also minus 1. And then the same for this one. Okay, so all the four possible states you can get if you measure a x, y, y direction for the first, second, and third electron, will always give you this correlation that the product of the measurement result is always -1. Okay, and then how you can get from here to here? Okay, it's basically the same as how we show you guys at the the 2-qubit right entanglement, how you get that, and then the detailed calculation is shown in the note, page 20 and page 21. Okay, and then I'm really looking forward to, like, some people can actually create this game. Okay, and then there are actually other type of game that you can design, and then specifically favor quantum mechanics. And hopefully one day, okay, I think the physicist who first invent this can actually try to do some, I don't know how you call it. It's the try to sell it to Las Vegas, okay, and then pretend it to be something classical, and then win some money, and then going on the well, they have a list that whoever won the money, okay, would not be allowed to enter the hotel anymore. But then hopefully, okay, someone can do this, and then it's kind of like a joke, and then we'll I'm sure it will land in the national news headline, and then people can learn a little bit about quantum mechanics and entanglement for the general public. Okay, and that's all for today, and I'll stay here for a few more minutes to answer some questions.